Give me one moment. Let's see. I think I asked for. Let's see. Wednesday, guys. Um and it's going to be at 1 p.m. on Wednesday, October 20th. And most probably, it's going to be online. I don't see how we can sort of go to school for this. So the reason why it's on Wednesday is because I don't want any problems with Moodle and so on. So I'll get the IT guys to stick around. And the main thing is they told me to tell you, you got to know your password and your login. If you know that, not a problem. Okay, so that is where we are. So mark the dates, and it's going to be a bit staggered randomly. So I'm going to send you the details uh, much earlier than that. So you'll know what to do once we begin. Okay, I just want to quickly jump uh, to kind of show you how unique pointers are built. But I believe I kind of didn't complete certain things yesterday. So let me start. Okay, I'll start at page 70 because it looks like uh, you know, we went through around 80 slides. So I'll start at 70 just as a uh, brief review of what we covered. Basically, we learned about R value references and uh, and they're declared as you can see here in presentation. Nope, there to no to 70. Okay, so this is the syntax. We're going to use this a lot for the remainder of the semester. We'll also use std move, standard move. So kind of let's make sure we understand what this means. So we spoke about L value references, const references, and then this is the third thing. And we spoke about how we can have the behavior of R value references is sort of completely opposite to L value references. L value references can bind to named objects, which is what you see with this one here. But they can bind to R values. This is an R value because it is a temporary object, has no name. It obviously cannot access to a temporary that has been instantiated, to satisfy this particular syntax. So there is a constructor associated with this C style string, and that particular object is going to reside somewhere on the stack, and R3 doesn't have access to that particular name. So this is not going to work. On the other hand, this guy cannot be bound. There is a way, and we're going to find out how to do that. But right now, this guy cannot be bound to a named object. Instead, it can be bound to temporary objects, the one returned by a function, or the one generated by the compiler to satisfy this particular constructor call. Now think about it this way. C++ compilers are going to work really hard for us. So when they see this, they're going to say, okay, there is a way for me to construct a string object, but that string object is going to sit somewhere on the stack and has no name. And this guy is going to become a sort of a life extension of that temporary. As long as RR3 is going to be in scope, then that unnamed object is going to stick around somewhere. The compiler is going to make sure that it exists. This guy works in a slightly different way. What it does is that it takes that unnamed object, defines it to be a read-only object, and makes this guy be a pointer to that object. So in a sense, this guy is also extending the life of this temporary, and this temporary is going to be around as long as CR is in scope. And all of these variables that we are declaring are on the stack. They are in a sense local. So they're going to go out of scope at a certain point, at which point the memory is going to get cleaned up. So in that sense, there's garbage collection taking place implicitly, right? That is what RAII means. Okay, so the basic idea here is that we want to perform some sort of destructive read. And the reason why we are extending the lifetime of these unnamed objects is so that maybe we can take over their resources. And how do you access them? Well, you access them like any other object. In this particular example, S is a named object. So S is an L value when used in an expression. Since this particular L value refers to a string object, you can use it just like any other reference or named string object. So nothing going on here. It's just that when S goes out of scope, which is at the end, you're going to have to imagine that the temporary object that S is referencing is going to sort of die. And we'll later on talk about, when we talk about move, that sometimes people tend to say, I want to extend the lifetime of this guy, and I'm going to use move semantics to kind of, have this guy continue to refer to the, unnamed object that S is referencing. So we'll talk about why that is not a good idea. Okay, so 3 types of references. Unfortunately for you, it's going to extend, sort of complicate your life, because when do I use what becomes an ongoing sort of like issue, right? Which I hope to kind of make sure everybody is able to kind of understand by the end of this week. So sometimes I tend to use these terms just like in the standard input-output parameters. So in other words, we take a reference, do something with it, and use it to give it back to the caller, the transformed object. This one, we just want to kind of perform get some access to the data, and maybe create new data, but certainly we can't change the object that this guy is referencing, this L value reference. So we label them as only input parameters. R value references are input parameters, but the idea is that we can perform the destructive read we spoke of earlier. We don't need to preserve, so we can kind of do something with them that will hopefully make our code be a bit more efficient. So the move constructor is sort of defined like this. And then we have there are a couple of different ways in which people kind of write. There are idioms. So I'll show you in a moment. But notice the idea here is that RHS is referencing some temporary object. And this is quite important. We are taking over those resources. And the standard is quite clear on this. The object must be left in some sort of a sanitized state. Okay? So if you forget this, then you're back to programming in C, because you are going to end up with 2 guys pointing to the same thing. So it's quite important that you set this pointer to a null pointer. And later on, you can assign to the temporary if you so want, right? So that is what I mean by sanitized. It's sort of, we are taking the object that RHS is referencing and we are leaving it in as though it contains nothing, an empty state. That is better, and I mean, not better, but that is what the standard expects from us. So this is the most important line where we are setting the pointer in the source to kind of point nowhere, and we are taking over all of the resources. So does anybody need any pictures to illustrate this? One way to kind of imagine what's going on is I can draw a picture. All right, so here you go. So str is an object that consists of, you've seen the string, it consists of a pointer, right? And it consists of, some number that, a variable that indicates how many objects are being pointed to by this particular pointer. So let's say it's some HELLO followed by the null, so it's 5. So this is what this object is pointing to. Now, RHS is referencing some temporary object that is located somewhere here. So this is a pointer, and Sly Fox is quick. So this is quite a big thing compared to what we have. And what we know with copy semantics is that we are going to perform a deep copy. So we're going to allocate memory somewhere here, perform a copy using, let's say, std copy, the STL algorithm. Once all of the deep copy was performed, then we perform a delete on this. It's only after we made a copy that we perform a delete. Otherwise, you're leaving your state with no guarantees if an exception was thrown in the creation of this particular block of memory. So then once we delete this, we take this pointer and point to this. And then obviously we update this data member, the length data member. So this guy is, let's say, 15. So this is kind of how things work. And what we are saying is that this guy is going to die. So why not take over this guy's resource? So you're taking this particular pointer, let's say, I'm not showing you the copy assignment, but I'm showing you the copy constructor on the slide there. But I hope it makes sense. So what we are doing is we are saying, okay, I want to get rid of this, and instead I want to take over this guy's property, and this guy is going to become the null pointer, right? So that's kind of what's going to happen. We are simply taking over without making any call to new and so on and so forth. And that is what the purpose of this no except is, to indicate to the compiler that it should switch off exception mechanism for this particular function, right? So that is what's going on, and it's quite cool because when you're dealing with large databases where there's a lot of copy going on, for example, sorting, then you normally tend to move things around. When I say move, I mean really copy. So now with the move semantics, we no longer have to make copies. Instead, we can just kind of change these pointers to point to the relevant data, and make the old guy become a null pointer, or maybe if you're doing the copy assignment, you're going to make this guy point to this object's information. So there's sort of like an exchange going on. And the idea with the exchange is that I don't physically need to delete this memory, because this guy, when it goes out of scope, or the reference goes out of scope, it's going to die. But some people don't like that, because uh, the thing, that temporary that we are talking about could be sort of again moved somewhere else and so on. So it can kind of go through life by constantly getting moved around. And so we never are sure when our hello string is ever going to be destructed. So some people, what they do is they kind of physically delete their memory and then make this they pointer point to the right hand side's memory, and make sure that the right hand side will have a null pointer. All right. So different people do it differently, and it's all about sort of the standard. All it says is make sure that this guy is good enough to be assigned to later on, if it is still alive. And if this pointer is null, there's nothing wrong with that. We can go ahead and assign. So different people, again, like I said, do it differently. Okay, so that is the um, sort of like the basic move constructor. And we have the sorry, the move version of the copy assignment. And what it does is that it, like I suggested earlier, it swaps the pointers. And uh, like I said, some people think, why should I delete it when the other guy can just take over my memory and just go ahead and do the delete? But the important thing is that any block of memory has only got one single owner, right? Which is one of the problems we are trying to solve. Double deletion, for example. No deletion is a problem, but double deletion is also a problem. Okay, so that leads you to kind of have essentially, if you are building a copy constructor and a copy assignment, obviously you're going to build a destructor. And since the compiler will not synthesize a move for you, if you have a copy, then it is quite important that you implement your own. All right, because if there was a need for you to build a copy constructor and a copy assignment operator with a destructor, you definitely do need a move constructor, for example. Why? There's going to be a lot of data that is going to be constantly moved around, especially if you're sorting big databases. Then you would rather not move. And I have a little piece of code here to illustrate the savings we get. Okay, so let me kind of show you some very sort of improvised code just to illustrate the point. So it's not sort of like industrial strength code by any chance, by any means. Okay, so what I did was I kind of thought, not to confuse you guys, but just to kind of complicate things a little bit, I created a template similar to the one that you did for the bit set, but this one is more to mimic a dynamic array. So it kind of looks like this. It's a templated class that kind of, I just call it vec in honor of our vector class, which is not an easy class to replicate. It takes years to get it all right. So this is a very trivial class, right? It doesn't do many of the good things that vector does. For example, I don't separate initialization and construction. So anytime I allocate memory, it gets default initialized at least. With the vector, remember, you can reserve memory, and that reserve memory is using an allocator, which is going to use malloc maybe to grab some memory, and later on when you do a pushback, it's going to actually instantiate an object in that raw memory, right? So I don't have that, and it's probably, I was thinking, a good exercise for you guys to do. So this is the very, very basic class. It has all the basic things: a copy constructor, copy assignment, and obviously pushback is such a critical thing, so I added that too. And every time we push back, we get new memory. So hang on, what happened to? Oh, so this is the implementation of the class. We don't have, as you can see, a copy constructor at all, right? And the pushback is also sort of copying using copy semantics. It makes an actual physical copy. So, and I'm kind of using the copy swap idiom that we spoke of last week, I think. And so then it's a pretty decent class, but definitely the problem with it is that I'm not separating allocation of memory with construction, right? So I always default construct, which you can see here. Okay, so this is the default constructor that is called anytime you want me to allocate some memory. Vector doesn't do that. When you say reserve, well, it grabs memory, but not using new. Instead, it grabs raw memory using operator new, and maybe operator new is built using malloc. So the memory itself is raw. Okay, so what I did then is I took our string class, right? The usual string class that we've been dealing with. Not much change since HLP2. It contains all the basic stuff, right? Now, what I did is I obviously did not implement any move semantics, nowhere, right? So we'll figure out how to do that in a moment. Then, to kind of talk about savings, I created some sort of like a silly thing, but it consumes a ton of memory. So this is a vector where each element is a vector. Well, our vector class is templated, so maybe I should have called it an array, my mistake. But the standard library vector is going to have is going to contain an element, or elements, where each element is our dynamic array of strings. All right. So maybe a picture might be useful to kind of picture the amount of memory that we are getting. So this is vector, and I'm not sure what I call it. The vector is, no, I should go to my source code. So it's called vector of vector strings, and I am reserving 10 of them. So the vector is going to point to this raw memory, okay, where each element is going to be a vec of strings, right? Each one of these is a vec of strings, and the memory is raw. There's no objects that have been constructed. So there are different numbers here, but for now I'll just put 10 because the size is definitely 0. Okay, so then for each one of these elements, 10 of them, I say build a vector, a dynamic array of strings. So this function is defined here. It's just a simple function that any one of us would write just to do some quick testing. So I have this sort of lengthy string, and what I do is I take the class that we built, a vector, templated it with the string class, and I said, you know what, give me a vector that can store, I believe, 1,000 strings. So it's pretty big. So this is going to be a vector of 1,000 strings. So how do you picture that here in memory? So this guy, I forget what it's called, result, is going to be containing 1000 elements, and it contains a pointer to a block of memory where each element is going to be of type string, right? String itself is a handle class. So it contains the length and it contains a pointer. And the default construction will make sure that this, I believe, is going to be some sort of a null pointer, right? So there are 1000 of these. So this is what it looks like inside the function. And what the function is doing is it is using the copy assignment operator to take this null string and add some information. Okay. So we are adding the same thing. That's fine because random. We can randomize these strings or imagine that we are reading from a file, but this is the simplest. So I'm filling this vector with all these big strings. And so this number is, let's say, 100. Big strings. Maybe they could even be much bigger than that, but let's assume that it's 100. So we got this. Okay, this function returns after having created a vector of strings, right? Where each element, which encapsulates 1000 strings. Okay. So now I come back from the function and I say, I want to take this vec string and add it to the vector. So I want to do this for all the 10 elements in the STL vector. So what that means basically is that all of this stuff is going to be returned by a function, and the returned stuff is going to be copied, and sort of this guy is going to then have the 1000, and then it's going to create its own copy of this entire stuff that you see here. I hope you understand the scope of what's going on. And then we are repeating this for all the other remaining 9 characters. So each one of these is created by the build string function, and then we return that. We hope the return value optimization will come into play, but still, pushback is going to make a copy of whatever is returned by the function, all right? And that means we are performing a deep copy. So we go through each one of these. Oh, you're a string, so I'm going to call the, first I'm going to construct the null elements because we are default initializing, and then I'm going to copy, I'm going to use the copy assignment to fill each one of these with the appropriate information. So there's a lot of copy going on. I didn't calculate, but when I compile the whole thing, I just print a number and it looks like this. So there were 40,000 assignments of strings altogether, copies, assignments, whatever you want to call them. And there were 30 copies of the vectors constructor, all right? So does everybody understand where these numbers come from? 40,000, 30. And some of your applications could be doing an equal amount of work. So obviously, I'm doing 10,000 default constructions of my string because I don't have the capability of the vector class. Then I do 1,000 calls to the string copy assignment operator. So that's 2,000 per element. Then I return them through that function. Let's hope there is uh, some sort of a copy being made. That's no RVO is kicking in, and it's saving us a lot of trouble. And then for each one of these 1,000 elements, the copy constructor is going to come in, and what it's going to do is that it's going to again create an array of 1,000 vec strings, which in turn will cause this to be double and this to be double, leading to 4,000 per vec string. And then repeat this 10 times, that's 40,000. Does it make sense? So there's quite a bit of copying going on because we don't have move semantics. Vectors themselves have move semantics. So if you do something like this, so I want to make a copy of this, and then we want to see how many copies were made, we can kind of run the code again and check the numbers. So move semantics did come into play, right? It tried, because instead of 80,000, it ended up only with additional 20,000. So the how do I explain this? No, you know, the vector class has move semantics, but it still has to make a physical copy of every single element, and that particular copy is going to require a default allocation that is going to be 10,000, and a copy assignment that's another 10,000. So even though the vector is pretty smart, we got quite a lot of copies, right? 20,000 still. So a very simple thing to do then is to begin by implementing the move semantics here, right? That's all we'll do, and see how much things get better. My computer has been giving me problems all day. So let's build the first one, which is the move constructor. It looks like this. Okay. Let's build it here, right here, so we don't have to go to the other file. And how do I do this? So this RHS is this guy, right? Is reference to somebody like this, who in turn is pointing to 1,000 strings. So all I want to do is take its pointer and make it my own and give it the null pointer. Okay, so that's exactly what we'll do. Pointer. Uh, and then we'll make this guy be the null pointer. That's it. Does this make sense, folks? So you're a handle class, and generally you have a pointer and a data member specifying how many elements. I'm going to essentially copy your pointer, the value stored in your pointer. I'm going to copy whatever is the number of values that you are dealing with, and I'm going to make you essentially become a null pointer. So now I'm going to now take over everything that you have in that sense. So this is the move part. Then we need to implement the other one, which is going to perform the move semantics when we assign. So here again, we're going to end up with something that looks like this. And I don't know whether anybody would do that, but from my understanding, it's kind of like become standard practice to do this, which is check for self-assignment. And I'll talk about what that means in a moment. So I take my address, compare it to RHS, and essentially swap, right? And there is already a swap, I believe, that has been built in. And so, I just swap my stuff with your stuff. And once the swap is done, we just return. So I'm giving you my stuff, I'm taking your stuff with the expectation that when you go out of stuff or out of scope, my stuff is going to go away using the RAII principle, because you are an object of type string, a vector, and you do have the implementation of the default constructor. So that's really all there is, all right? These two guys, and let's see how much work they save us, because from the picture, what happens is that rather than making a copy, if the vector class finds out that this vec string is able to participate in move semantics, then it can say, you know what, I can move you, right? Just like the vector guy was able to move the string stuff. So let's go ahead and find out if that actually is going to work. So I compile again and run, and we got some pretty good, decent savings. I think most of the move semantics came in with the uh, to actually check this. I'm gonna just comment this out to find out how much came. So we saved quite a bit because we were doing 40,000 copies and assignments, and that got reduced to 20,000. Because what's happening is that when we say pushback, this guy, which has this pointer here pointing to the array of 1,000 elements, this guy is coming in and taking over that pointer. And so there's no need to perform any of these additional deep copies, right? So right away, the amount of work that gets done has been reduced by how much? A factor of more than half, right? From 40 all the way to 20, and vec copies fell from 30 all the way down to 10. And so the benefits are pretty good in terms of implementing move semantics, and you can implement them in lots of other functions that you may have. For example, there is the pushback. So you are copying. Well, if in the future, if the type T implements move semantics, then you can kind of actually do this, right? So it's not just restricted. The move part isn't just restricted to the constructor and the copy assignment. You can go ahead and implement it for anything. So we got those savings, and then there was another thing I wanted to show you because we were talking about it last week, and this was the code that is familiar to you. Right? Remember, I created, I call a function f, and in that function, I define this vector of strings, and then I reserve. So there are no construction of string objects. There is one string object that gets created. I'm making a copy of this, so a second string object gets constructed. Then I'm creating a new string object that is going to be data. So that would be the third one. And if string had move semantics, again, the pushback function in the vector class, just like this one that I showed you, would be overloaded to take R value references. And what that means for us is that the pushback is simply taking over the memory that has been created by this temporary. And this is the one that we're going to talk about next. We sometimes can recognize, it's not just the compiler that recognizes R value references. Sometimes we say to ourselves, hey, this particular guy, which is an L value, is going to go out of scope. But can I take over its memory? And that is what the standard std_move function does. It doesn't really move anything, but it changes the type associated with S from an L value in the expression S to this entire expression after the move, becoming essentially an unnamed a reference to an unnamed R value. So essentially, the std_move uses some template magic to convert the object that is of type string to become a reference to a reference to an R value. In other words, an R value reference. And R value reference is, can be moved from, and so we do the move. So essentially, all we have done is 1, pushback 2, and the temporary 3. We created 3 and no more than 3, and everything else that we do is simply going to move around that original data that got created. So we have a vector, we default initialize it, and we are testing it with assignment. RVO does come into play here too, because you're returning W, and traditionally the system will make a copy of W, and we don't have access to that. And that copy would in turn be used to assign to V. So RVO, which is now part of the standard, says, you know what, we don't have to do any of that. And V, because F, remember, returns by value. So the compiler will recognize, we don't have to do anything. If it can do RVO, then it recognizes the fact that this entire expression evaluates to a R value, and therefore the compiler says, hey, I don't have to make a physical copy of whatever is the object that F is returning. Instead, I can implement move semantics. And so the final count here, using that same string class, should be exactly 3. So let's try that out as a one last test to show everybody that this stuff does work with minor changes. What the heck? Oh. Okay. So we have 5, right? So we've learned something. The vector class is going to work really hard to get move semantics in. But if the string class doesn't do any move stuff, then we have a problem where we have to just resort to copying. So let's go ahead and just quickly, just like we did with the other one, build the move semantics. And it should be fairly easy. So this is the copy. And for the string class, basically, I don't know what the data members look like, length and pointer, right? So I'm going to take over length from RHS. I am going to take over RHS's pointer. And in this particular scenario, I'm going to actually do a delete, because I don't want my stuff to kind of be moved around. I want a much more deterministic behavior, which is the memory is gone. And we kind of do something like this. Hang on. So my okay, we have a problem here because I copied length, but pointer now I lost track because seemingly here I'm creating a certain block of memory as the default, right? So I'm going to lose that. So I need a better way to do this. And member initialization, I don't think is going to work. So we'll do, no, if I do this, what happens is that the compiler actually won't initialize length to 0 and it won't allocate memory. If you don't have this, then the compiler will first initialize these members with the default values that you specify when you define your class, and then do the work inside the constructor. But here, if you actually specify things in the member initialization list, the compiler won't take part in this initialization process, okay? I'm quite sure of that. So what we can do then is simply take over the right-hand side stuff, and the right-hand side is got to be made to become the null pointer. We don't want to do any delete. Instead, we simply say you are a null pointer, and that's it. Okay. And actually, I'm sorry, but let's do all this outside. And then the other thing I forgot with the vector class, which I'll go fix, always make it be no except, okay? Quite important. And then we'll build the move assignment. So it's going to look like this. And here, this is quite simple because there's no such thing as member initialization list. So I take my address, compare it to the right-hand side. If they're not, no, what am I doing? If they're not the same, then I'm going to go in and take over, right? And I believe there should be a swap function, right? Because if you want to implement the copy swap, every one of your classes should contain your swap. And so I'm going to go in and do the swap, and I'm going to swap with the right-hand side. That's it. And once you're done, then you just say return this. So I'm giving RHS my stuff. I'm taking RHS stuff. And if you don't want any of that, you don't want to participate in any of this using the standard idiom, that's fine too. What you can do then is you simply say, I want to take over the length. I want to delete my memory, right? Nothing wrong with that. And then I want this. In other words, I'm deleting my own memory and I'm taking over your memory. And I want to make sure that you end up looking like this. And I put the no except because there's no way any exception can be thrown. We're not asking for any resources. We are in fact giving up resources. So rather than the swap, what you want is a more deterministic behavior where you know for sure that the memory that you created isn't just going to go move around and at some point later on get deleted. If you're building, in the back end and there are going to be large number of players, well, maybe you want to claim the memory associated with each player right away rather than wait for whenever the right-hand side goes out of scope, which could be, if it gets moved around, maybe it may take a long time. So we have lots of player memory that doesn't get deleted. It will get deleted, but not yet. While here, I'm making sure that the player stuff gets deleted physically by me, right? But I don't allocate any memories. So that is the thing. Does that make sense, guys? So I believe everything is good. Hang on. I again build this inside the class. Okay, I mean, let's just build it. Okay, some of you are going to get confused about where the no except should be. There should be no confusion. Right away after the function, you go no except and then continue with your member initialization list. So length is going to be this, then pointer is going to be this, and then then we just no, not delete, set this guy to be null pointer. Okay. And to make sure that everybody's convinced that I'm not playing fast and loose, we want to make sure that I just copy and paste this part so we know that we are keeping track of every single object that gets constructed. Okay. And we do that here. Don't think I do a copy here. Or maybe I do. I have no idea. No, I don't do a copy here or an addition. So I'm gonna skip that here. Okay. Well, we have the entire thing. Hopefully I didn't screw anything up. And we should see no more than 3. What's going on? Am I changing the right file? Because we are supposed to be moving. Not increment that. Okay, my mistake. So the actual copies, the physical ones, right, are 3. I'm not counting the move constructor because, we're not really constructing, allocating memory. It's not supposed to be expensive. It simply does this. And same goes with this guy. We're not allocating memory, copying. See, because every time you allocate memory, you got to fill it out. So there's quite a lot of work that goes into filling up memory. And so we're not dealing with any of that. So what you have now is the vector class showing move semantics, the string class in support having move semantics because it's going to be an element of this vector class. And together, they're doing the minimum amount of work and making sure that things that are already allocated can simply be moved around. So that is essentially the rule of 5 and all of these work. Any questions, guys? So quite simple and straightforward. The only thing I think we need to kind of just talk a little bit about is std move to see what it does. And so the compiler takes care. It can see when a function is receiving or is being assigned an R value, right? That is the whole point of having that extra overload. And we went through that in quite some detail. But for this particular scenario, we did something sort of strange. We said you compiler wouldn't know, right? That S being a L value expression is going to die. So I am going to intercede and instead tell you to use move semantics rather than copy semantics because I know something about this L value's behavior. Now, obviously, if you actually do something like this, right, your program should get you should get some major error. So if I compile, yeah, um, you know, it crashed and burnt, right? So you left that, remember, in that indeterminate state, in an indeterminate but still sort of safe state. And it's your responsibility to make sure that you don't do anything with it, right? Now, on the other hand, you can certainly do something like this. And I had, okay, see, S, I'm going to assign to it like this. and things should be good if your class was well designed. So we left it in that state, but it should be recoverable from. The main thing is when you write your move functions, just be careful about this part and test it like I did right now. Okay, so we got that part, but sometimes, so this is all the compiler doing its job, right? S is being constructed using some conversion constructor associated with the string class. Then S2 is being initialized using a copy constructor. S3, obviously here you can see that we get an L value, so the compiler is going to do the work of ensuring that the move constructor comes into play. Right? Now, here's a slightly more sort of complex stuff where we have all these overloads. This takes what we call an in-out parameter by reference. This is an in parameter, which is, you know, a read-only reference. And this is an in and move from parameter. So imagine you have a function g, and g is receiving a reference to vi and a reference to cvi, right? One is read-only, one is a in-out parameter. So when you call foo with vi, one has to be quite clear in terms of what is being called, right? And the compiler will do the work of making sure, since vi is an in-out parameter, it will find the best match out of these three, right? Because from HLP2, you know that finding out which function gets called through function overload resolution is complex. And then when you throw in templates, it gets unnecessarily complex. But these are just great for, you know, things like midterms, right? So clearly, foo is being invoked for this function one. CVI, obviously, I mean, it shouldn't take much thinking to say, okay, 2 is the best fit, right? And the compiler in this case, right, if 3 didn't exist, can certainly use 2. But since 3 exists, that is exactly what it does. And that is what we get in terms of help from the compiler. It is able to switch if you define 3 between true and 3, depending on what this particular parameter is. Don't forget, 2 is the catch-all. It can actually take everything. The function g will work if you get rid of 1 and 3, right? Vi is going to be obviously converted to be a reference to a read-only. CVI, reference to read-only. And this temporary is also going to be mapped to a reference to a read-only. So we learned that all 3 functions will work with just 2. But in the presence of 2 and 3, the beauty is that we get that switch at compile time that allows the compiler to decide which function should be invoked. And so in the cases that I just explained, the compiler knows what to do. In other cases, you have to tell, okay? And there are many situations where the compiler is not going to be able to help you. I have actually a very good example. All of you know about the swap. In fact, the swap looks like this, the standard library swap. If you actually look at it, I didn't do any different than what the compiler or the language does. So we have the swap function. You can see that there's not a whole lot going on in terms of since C11, right? We have the usual references, and this one became no except. I'm not sure what they do inside to make it be no except. I suspect something, and I'll show you what that is, right? No except means the author of this particular function is so confident that there will never be any memory allocations, deallocations, or any such resource allocations, not just memory, could be anything, right? So what makes them so confident? And it says since 11 until 20, and then since 20, I guess we have const expression functions, right? Just to speed things up maybe a little bit. So how did they go about making this function be better than what you see here? Well, clearly, what's going on here is not so complicated to see, right? Let's visualize this. There is a some fancy object. There is B, and what we did is we went and made a copy of temp or of A. So there are two versions of A now, temp and A. Since there are two versions, what I do is, and notice the construction took place through a copy construction. So there's an entire replica, a clone made of A. Imagine A contains the vector of dynamic array strings, the one that we built. That is going to cost you a little bit just to swap things around, right? Quite a bit of stuff. So there was a copy made, so I'll label it as temp/A. Then A is going to be replaced with B using a copy assignment. So essentially you're cloning B here, right? And there are two versions of B. So the original B says, you know what, I'm going to become a clone of temp. So how many copies did you make? Constructions. So you call the copy constructor, copy assignment, and depending on how complex your data is, it is going to be fairly expensive. But you know something that the compiler doesn't. And what is it that you know? Well, we know that if A was a handle that is pointing to this memory, right? This is A. Then we don't want temp to make a clone of this entire memory, right? So why not make temp point to this memory and make A, let's say, be the null pointer. Okay, so we don't construct. We have only one sort of copy of A, right? A shallow copy of A, because this entire thing is just a replica of this. And then we went in and made this not be exactly a replica by making this stuff be the null pointer. So we end up with this here. Then when we end up assigning the B stuff, we know that B must contain A stuff. So why? Why should we not use what B has as its data? So if B contains this data, right? Why not make A, which is null pointer, to take over this and make B be a null pointer? And then when we come here, why don't we make temp, make C become a B, excuse me, become a copy of temp. So this guy now is going to point here, and this becomes the null pointer. So what we did is that we did swapping, but without using the analogy, because I remember in HLP1, I used this analogy. I have two paint cans, right? Red and blue. And I want you to switch. Well, we need a temporary can. And we take the temporary can, pour A's color into the temporary. In computer memory, we have two copies, but in the real world, A got emptied out. So this move semantics actually mirrors what happens in the real world. And for a long time, we couldn't do that, but now we can actually replicate what happens in the real world. Because when I pour A's contents into temp, A doesn't have anything, right? And if you imagine that the contents of A are sitting somewhere, then all I need to do is make temp claim ownership, while A disclaims its ownership. It says, I give up. I don't want this anymore. So many things can be made better. So the swap function, I presume, unless somebody opens up the standard and maybe they talk a little bit more about it, but my suspicion is that since 20, if they made it be no except, it means they're doing what we just did, right? Which is they are saying, you know what, there's going to be no constructions taking place, no memory allocations taking place. All we are doing is just kind of, performing shallow copies, and therefore there's no chance of an exception ever arising, right? And so the only thing that we do is we have to call the default destructor associated with 10. So does it make sense? So that is the problem that we also need to solve. So one way to solve it is to simply, be a little bit sort of, if one is not so worried about the syntax, essentially I'm taking an L value and casting it to be a R value reference. Essentially, that's what it is. And when the compiler sees this, it says, okay, what I have is an R value, a reference to an R value. So it's going to kick in with the move constructor, the one that we just wrote earlier, right? And that move constructor is simply going to take over A stuff and leave A in a sort of like a safe state. But it's a hollow object, right? It doesn't really contain anything. We repeat the process. So we take over the type of B and adjust it to initiate move semantics. So the compiler here says the right-hand side is a reference to an R value. So I'm going to just go ahead and call the move copy, no, not the copy, the move assignment operator, and repeat that process. So that is essentially what the C++20 stuff seems to be doing. So the thing is that sometimes people get confused, right? Well, what happens if I don't have move semantics in the object T? Like for our string class, we didn't build move semantics until today morning. What happens? Is it going to work? Is it not going to work? I want you to think about that, right? What happens if this is an R value and the particular function you have looks like this? Right? And you're an R value. Can you be associated with this guy, guys? Can you be passed as a reference, or do you get a compiler error? So one of the things we learned on Tuesday is that this guy can be thought of as a universal type, right? Anybody can be made a reference. Or this a variable of this type can become a reference to an L value, can become a reference to an R value, can also become a reference to a const reference, const object. So if the move constructor is absent, instead the compiler sees only this, then it's going to say, alas, I have to perform a copy, right? So on the other hand, with our string class, if we built the appropriate functions, then the compiler says, okay, I see an overload which looks like this. And I'm going to go ahead and call this, right? So that's kind of what it is. So the problem, though, notice I use the term perfect swap. And this is going to become a problem for you. For people who write the library, not so much. In your case, application programmers are going to have some issues here. And I'll talk a little bit about that. So use of static, hang on. Okay. So use of static cast becomes verbose. As you can see, it's pretty ugly. So who wants to, write all this stuff, right? Unless you want to impress your boss who programs in Java. Otherwise, I mean, that's what they did in the standard library with a little bit more sophistication, because move contain does something a little bit deeper, but I think hopefully everybody gets the idea, right?
Studying Mu again takes an entire week, so this is good, right? And if you want, you can study that about what they do, because we have to start digging a hole, deeper and deeper and deeper into understanding this. And you should, and this is one of the more important things in modern C++, this whole idea of moving, right? Now, again, I use the term almost perfect swap. I'll talk to you about it in a moment. The problem with this particular swap function that we wrote, and that is part of the standard library, okay? Let me show you the standard library, is that, all of them take references, right? L value references, and nothing else is going on. So what um, what what happens if I need to do some swapping where the right parameter, for example, for the string class, was obtained by adding two other strings. And all of you know that the overloaded addition operator for the string class returns by value. In other words, it returns an R value. But this swap in the standard library says, you know what? I take L value references, not R value references. So what to do? So what used to happen when when people started using Mu semantics, I mean, it was quite exciting because most of a C++ programmer's life before 2011 was in figuring out how to save a little bit here, a little bit there because of all the unnecessary copies, right? And suddenly with Mu semantics, all of that goes away. So, uh, so but they wanted, you know, things like this to use Mu semantics too. And the compiler is going to flag this as an error because the right hand argument is an R value. Does everybody understand that, guys? Because it's a temporary, right? It is a temporary object that has no name. And so it's only visible in the scope. And the swap, unfortunately, says, no, I want a reference to a name. So, and actually, I used to do this, but even for class stuff, but I stopped because it's just too much work, right? To kind of write lots of overload. So notice my basic swap now, I had to overload, with additional parameters. So in our case, we may end up with three, because there are two parameters, we may end up with three overloaded functions. What if you had a function that takes five parameters? The combinatorial explosion of all the different functions that you have to write is what led people to kind of, think about how best to use Mu semantics, right? Do you guys understand my problem? Let's say you're working on the back end of your game and you want to store a player's information. So at the minimum, a player is going to have their proper name and then some sort of a game nickname and some additional information about stuff, right? So clearly, you know, if you want to deal with a player in terms of economy, money, whatever, we are looking at 4 5 parameters. And you want to optimize this because you don't know, right? It costs a lot of money to get the cloud stuff to work from Amazon, and your bosses keep pushing you to get everything be more efficient so that they can spend less of the income on the cloud service. So you essentially are going to have to write 2 raised to the power of 5, potentially, tens of different overloads, and that makes it obviously complicated to get the full benefits of Mu semantics. So it's all up to you, right? If you think that writing the swap is enough, what I wanted to show you is that in general, it's not. A lot of our application code it doesn't necessarily swap like the standard library, a left-hand side and a right-hand side. We may wish to swap lots of different things, right? In one go. We want to store player stuff. So I need to create a player object. So I have a string for middle name, last name, initial, other kinds of stuff, nickname. And so in some cases, we have move semantics kick in, and in other cases, we don't have move semantics, and it all defaults to copy construction. So you're not getting the benefits until you write all of the appropriate overloads, change the way you store player stuff, right? And that could be stuff that was written by lots of other people, and you may not have access to that. So sometimes it's not so trivial for you guys to take what the standard library does and put it into your own code, just because of the standard library. They implement the vector class. They spend years worrying about how to make it be good, but that's it. All right, and I can actually show you something to kind of give you a sense of the vectorial, uh, maybe sort of explosion, right? If we go to the uh, uh, container library, so let's say we look at the vector class. I think it overloads. Uh, so let's look at one of these, right, to see if there is that combinatorial explosion. So one, two. So do they have an R value? Does anybody see R value? No. So equal to. So I'm comparing uh, L value references. L value references. Oh, these are all different functions. So they just do this. They decided not to do that. But so in other words, they said, you know what? If you want to compare an R value with an L value, we're not going to help you. So which means you, the programmer, is going to essentially do that work, right? Because the standard library, for some reason, I thought they would do it, but I guess not. So, but in other places, they do it. So if you look at the pushback, so there is an overload that they implement, right? So they added an additional function. So I'm not sure why they decided not to do that for the other one. So there are, as the English say, a little bit of a slip between the lip and the cup. So there is, it's going to be quite a bit of challenge for you guys to kind of imagine how to get in the process of getting your entire code to work. And if your code changes on a daily basis, which is what happens with games, at least from my experience, then it gets harder and harder. So uh, so we need to kind of you know uh, I don't know, either decide to have lots of different swaps, just for the cost, right, of making copies. So in this particular case, if you don't provide the overload, one, it won't compile, and then what other programmers who use the swap function will have to do is they'll have to convert that temporary. They can't write code like this. The temporary has to go sit in a L value object. So all of that is going to cost, and so one has to decide which is the best way to go. So when I say standard library takes this approach, I meant to say the pushback function, but I'm not giving up that easily. So if I show you let's go to look at the strings library. I think that's kind of what we do, right? Basic string. So I want to look at, they have a whole bunch of overloads. So let's look at the plus, right? So one, two, so they have, look how many, 12 functions just for the addition, right? That is what I decided not to do. So for some reason with the string class, they decided to do it, but not with the vector class. So the explosion in terms of what you need to maintain. So in your case, for the player object, you may have to have all the different combinations to get the best possible performance from your compiler. But maintaining this, just looking at this gives me the creeps, right? Look at the amount of stuff, and after if something doesn't work 2 years from now, then who wants to look at this stuff, right? You have to get an intern, and you know, it's so that is what I'm getting at. So C++ does it in some cases, and other cases it doesn't. So you can then tell the compiler uh, when you want R value references and when you don't using the move. Okay, it's quite a useful and quite an important actually uh, function. Now, when we talk about templates, we're going to use something called std forward. And so it is going to use many of the things that we learned about, but move is more useful in a general setting, while forward is what makes in place back better than pushback, right? And so if you understand why that is so, then maybe when you write your own code, you can sort of do things better. Okay, any questions about the move, guys? A lot of it is pretty standard. It's just that you need some experience using it in your own classes, and then you have to do quite a bit of reading to kind of understand how things work. C++ is a rabbit hole. Once you go down that hole, it's going to be hard to come back up, right? Because it's on and on and on, and it is perfect for people who are finicky and that kind of stuff. So, anyways, uh, these are the useful things, and then it seems like we have something called unique pointers. So I kind of actually was going to talk about the pointer stuff right after this. Uh, so um, what happens if we try to swap objects of type that don't have move functions? We copy and pay the price, right? So one last time, all of you should know, how does the compiler evaluate movex to call to a copy function if it can't find the static, right? Because doesn't move x mean R value reference? So I'm going to do this one last time. So we can write 4 overloads if you want to pass an object of type X. Obviously, if you provide the first overload, you're going to have problems. So I cut that out. Why? Because you can pass if you imagine an int can use function one. A int variable can also satisfy 2. It can also satisfy 3. But 3 is not as tight as 1 and 2, right? And so the compiler is going to say you have a problem picking between 1 and 2. But if you get rid of 1 and you just want to pass an int variable to foo, then the compiler is going to pick the first one, because that is the most suitable if that particular variable is not const. If the variable is const, it's going to pick 3. If you pass the literal 3, it's going to pick 3, and so on and so forth. So we kind of have a good idea of how things work uh, for from HLP2. So now I want you to imagine all the 3 functions that you see cancel out don't exist. There's only one function. And that is what you have so far. Maybe in your internship, you have to maintain somebody's code, improve that code, and so on and so forth. So then right away, when you see that there is only this function, then foo can only be called for L values. It doesn't matter what you do, it cannot be called for anything else, right? So if you have an integer I, that is the only thing. If you have the literal 5, it's not going to work either. So if you, let's say, have the function number 3, the in parameter, right? Which is what you use if you have some really expensive stuff. Obviously, if you have very inexpensive stuff, you're generally asked to send things by value, okay? And what are the things that don't take up much? From what I understand from Strustrip, his blog, anything less than 16 bytes Maybe we have to look at the cache line and do some sort of research. For example, cache lines on the Pentium could be 64 bytes worth, right? So even if you ask for anything, well, it moves 64 bytes. So then in that case, it doesn't really matter, right? If something is worth only 64 bytes and it's all contiguous, maybe we don't need to deal with any of this stuff. Just get it, right? By value and be done. But if it's really expensive and it doesn't use the uh, sort of like you have a vector, a really big vector, and you want to pass it by reference, number two, that's a problem. You want to pass it by number one, that is still a problem because you're making some unnecessary copies, right? You're calling the move constructor and so on and so forth. On the other hand, if you just pass three for really big things, it's sort of considered to be free in C++. There is some overhead, but minimal. So in that sense, if you have number three and nothing else, foo can be called for L values and for R values. So which means this is the signal that the compiler is looking for. If you don't implement move semantics and you say move in your swap, well, the object of type X is going to be copy constructed, guys. That's what this particular slide is saying. Now, if you implement 2, 3, right? Hang on. That doesn't make sense. I think I meant to say 1, 2 or 1, 3. Okay, I got to fix this. I think what I meant to say is this and this is not. So made a mistake here. Let me just fix it. And so you're calling these two, or you're calling 2 and 4. Okay. I think that's kind of what I meant to say. So if you implement,
Professor, can I check why is one you write inexpensive and for three expensive?
because you're passing by value, right? In one, you're making a copy.
So shouldn't the one be expensive and three be inexpensive?
No, what the comments mean, use it for inexpensive stuff.
Okay, yeah, I thought you meant the one was less
No,
expensive.
no. Use it if you have inexpensive. And as you will soon see, smart pointers are normally moved around by value for that purpose because they're considered lightweight. For example, your iterators in the STL algorithms, we pass them by value because it doesn't cost you a whole lot. Adding references only complicates the thing. If you are bigger than 4 ints minimum, I think there's nothing gained by using references. So if you are point structures, all that other stuff, you just pass by value, right? And of course, do some profiling. And I think if you are doing anything using references as a default, you shouldn't, right? And hopefully, if these slides help you kind of think about those things, then that is good too. So if you implement 3 and 4, or 2 and 4, then obviously you can distinguish between L values and R values, right? And the compiler will do the right thing. If you have an R value, it will call 4 in either case. If you have an L value, well, in 3, it's going to in the top one, it's going to use 3. In the bottom one, it's going to use 2. Now, what if you have const? Well, unfortunately, you can't have the bottom work with const, as you can see, so it has to be only the top. Now, if you only implement R value references, then obviously the only thing you can do is call them with R values, but not on L values. So I think these slides are quite useful for you guys to understand function overloading and this whole sort of topic that we've been discussing. And so you shouldn't worry about what happens if I use move, but I haven't completed my move stuff? Then the copy semantics will come in. Okay, so I personally, for small things, don't write things like that, right? You shouldn't pass small things by reference clearly. You should, I think, pass them by value and use RVO, right? Remember NRVO? NRVO
Wait,
kicks in.
so small means smaller than the size of a reference, which is 8 bytes, right?
No, I think around anything less than
4
16
bytes.
bytes, and you should even profile it for 32 bytes. So for example, a 3D point, right? If you have X, Y, Z coordinates and each requires 4 bytes, maybe there's nothing gained by doing any reference stuff, right? Just pass it by value. Now, what if you have a color and a point? I think a little bit of profiling will help you decide on your machines. With the cache lines improving, I mean, 64 bytes, I believe, is what the minimum amount of data that is fetched and read from and written to the highest level cache. L3, I believe they call it, right? Or L1, I forget. But, so maybe you can pack everything and get no loss, and your syntax looks better, right? So I, many years back, I kind of prefer writing, functions like next the way I write it, right? It makes it easy for me to kind of, the whole thing is literate. Um, and so I think we saw this earlier. Uh, we saw this earlier. So so the last stuff is how do we choose and what is this page number? Well, basically, he actually now has a pretty nice blog. Actually, let me show you guys the blog because everybody, if you're a serious programmer, should look at it. Obviously, first of all, you should go to this place, right? So it tells you everything about C++ that you need to know. But what Strustrip did is he's kind of, I mean, I guess he's the one who's kind of sort of saying that this is the proper way to use C++. I think he's doing it because people have been complaining that the whole language is just going nuts, just too complicated, right? So I believe in functions, right? He talks about, I mean, sometimes it's a little bit dense, but it's good for you to kind of start kind of knowing what other people, your boss maybe or your colleagues, what are they, where are they getting the information from? So here, uh, he has some conventions, right? And uh, and he encourages certain things that you should do. And there are some guidelines, right? And guidelines are essentially if sort of headers that they have written that come on top of your compiler and tell you, hey, you're not following Strip's guidelines, right? And sometimes it can be annoying because there is certain ways you kind of do stuff and certain other things that make more sense to you. So that's why I don't kind of get inside and talk about these things in class because there is no one way, in my opinion, right? Just because TrueStrip says something, I'm not entirely sure if we should take everything just like that. If you're working on consoles, a lot of that information may not make much sense, right? So embedded maybe doesn't make sense, but it gives you an idea, and that is the most important. So this particular thing that you should look at where there are guidelines and essentially that's what I mean. So he took that stuff from his book. I'm not sure if you know, but it's a book that I think is like a weapon of mass destruction, to be honest. It's the C++, but it's old. it's 11, so it doesn't have 14, 17, and 20. But it is, if you hate falling asleep or can't fall asleep or whatever, well, this is good. Just don't drop it on your toes. Uh, and so on, that is the page that I'm talking about. It's a good book, but uh, you know, it, it's heavy. So what does he say? Well, basically from his guidelines, use pass by value for small objects. Use pass by const references to pass large values that you don't need to modify in parameters. We know that. Return a result as a return value rather than modifying an object through an argument. Why? Because the very first thing that happens is that your compiler is going to trigger return value optimization. Okay, it was iffy, but from 17 it is always on, and it's a great thing because you don't even need to do any moves in many scenarios. The compiler is taking care of optimizing the whole thing, right? So returning is quite an important skill. Many students just go use the HLP2 advice, just do the in stuff or the not R values. So these are in order, okay, of preference. You want to pass by value, that's the best. Pass by const is second best. Return, if you have to return anything, use R value references to implement move and forwarding. We'll talk about forwarding later. The last one is this dangerous thing. When you pass by reference, a lot of people in the establishment you're working at have to pay really close attention to that particular code, right? So it comes, that's why at the bottom. And, sometimes, especially with smart pointers, there's no particular reason to pass a smart pointer to a function if the function doesn't care about the smart pointer, it cares about the data. So in those scenarios that you are obviously sure of, it's better to pass a pointer, right? You don't want to pass a smart pointer to a function that does, lowercase to uppercase or does some stuff to HTML pages and so on and so forth, because you're making that function do a little bit more. One, you give it a smart pointer, it has to extract the raw pointer and then do stuff with the raw pointer and maybe put back the whole thing. Instead, that function is best written if you give it the raw pointer, C style or C++ style, right? So that is okay. I'm not sure why I'm getting it again, but these are the rules of thumb, and I think they're pretty good advice because you do the if you pass pointers around the least, chances are your code is going to be stronger. All right, so the next thing I wanted to talk to you guys about is smart pointers. What is the time? Okay. So basically the idea is that if you guys recall the file pointer that I showed you, well, the file pointer was an encapsulation of a raw file handle that we get from C, right? And a raw pointer is actually not that different compared to what we did in class. I mean, it's going to take a little bit more work, and so it uses the RAI idiom, basically takes your raw pointer and wraps it into a class-based object that has a constructor that will initialize the pointer with the memory that is returned by maybe calls to new or delete or new array or delete array. No, I shouldn't say delete array, new or new array, okay? And when the object goes out of scope, you don't need to worry about, did I call delete, all that stuff we spoke of in HLP2. I have a document that says these are all the things that can go wrong when you use dynamic memory. So none of that is possible anymore if actually your entire code uses smart pointers and there are no raw pointers anymore. So if somebody goes and searches your code, well, the millions of lines of code, there is no actual calls to the operator new, nor are they calls to delete. Instead, we are taking advantage of smart pointers. And smart pointers come in a couple of flavors. So they had this thing from 98 that was sort of like a pointer that wanted to have the move semantics, but there was no such thing as an R value reference, right? So it was good in some things, but obviously if the language doesn't support move semantics, then it's hard, right? And so the remaining three, the main idea here is in terms of ownership, right? So the unique pointer basically is meant for example, the vector class that I wrote, each object of a particular a vector object, I should say, is going to be the owner of the data uh, pointer member. It's not going to share with anybody else, right? So in other words, if you're building a vector or a string, or you want to store your player information in some sort of a container that you designed and built, that is what the unique pointer is meant for. Basically, the object that is instantiated from type unique pointer is designed so that its copy constructor and the copy assignment operator are deleted, right, as part of the design of the class, which means you cannot make copies of this particular pointer because double deletion, if you go back and read the things from HLP2, double deletion was a big problem. Right? Two guys pointing to the same thing inadvertently, and one guy deletes and the other guy doesn't know anything about the first person deleting, and so we have a problem. So I'm going to talk about those in a little bit more detail today. Shared pointer, basically, this is quite useful in databases. A simple use case is, from my perspective, is uh, we read a lot of data for games, right? And there's a lot of data, all kinds of different data. There's audio, there's animations, there is geometry, and quite a bunch of data related to the actual graphics, textures, and so on. Now, so if you are building a game engine, the way you want to store uh, the the objects in your scene, maybe in the form of some sort of a let's say arc tree, right, or a BSP tree or something like that. And maybe your AI system has a completely different way to subdivide space, and it wants all of the active objects in the scene to be organized, maybe using some sort of a graph based on a geometrical knowledge of the environment. So if you are in your house or in the campus or someplace, somehow you are going to write tools that allow yourself to essentially create a snapshot of the environment. How are the rooms connected? Do rooms have windows? What can I see through those windows? All of that is going to change on a daily basis because artists are creating new levels. And so you have to write tools that allow you to grab the 3D model, the 3D scene in a sense, and capture information that allows the AI guy to say, hey, I'm standing in this room looking in this direction. What portion of the scene is going to be visible, right? And if you are obviously trying to make intelligent objects, the more information they know, the better they can behave. So they need a different organization. So the same object that you obtained by reading some files is sitting in the heap, right? The actual data, but there are many different objects that want access to that particular object. So you don't make multiple clones of that. Instead, you're going to have different vectors, trees, lists, etc. Contain pointers as the elements, and they are going to then point to all of these different objects and organize them in their own way, right? Collision is going to be different. Culling is going to be different. AI is going to be different. Physics is going to be different, and so on and so forth. So essentially, the problem is going to be like this. We are very environment friendly. So all of us walk into a room and the first person in turns on the light, and we need a system so that the last person, it's a big room. So there are lots of desks, there are corners, I don't know, and maybe even many rooms, many exits and entrances. So I can't see who's coming, who's going. So we need a system that says the last guy out is going to turn the lights off. And when the lights get turned off by the last guy, the object that was defined in memory, right, when you loaded up your scene or whatever, is going to find out, hey, there's nobody else who is pointing to me, so I am going to go be deleted, right? So that is what a shared pointer does. It uses this analogy of all of us walking into a room, all of us need to leave a room, and the last person who leaves the room is going to trigger certain actions that will entail that that particular object is going to be garbage collected, which means it's going to go away, right, automatically. And this is quite important because maintaining all these data structures is hard work. And when you load up levels and lose levels, especially in consoles where the memory requirements are fairly strict, people just can't buy better memory, right? More memory or whatever. So for the next 4 or 5 years, even the games you're going to work on today and the much better games that you're going to work on, they're going to only require more data, but somehow there's not enough memory. So these happen a lot, and so shared pointers are essentially uh, packaging of this analogy that I just gave. So one way to kind of think about how all of us can ensure that the first person turns on the light and the last person turns off the light is maybe to use a cookie jar, and each one of us gets a counter. So you'll hear the term reference counter when I talk about these things next week. And so you come in, the first guy finds the jar empty, puts his cookie inside it, maybe think of it that way, and turns the lights on, right? Because the cookie jar is empty. Then the next guy comes in, drops his cookie, right? Because we need to know at any given time how many there are. And so, but this second person doesn't do anything in terms of turning on or off because there's already something there. And so I'm going to just drop my cookie. Well, and it continues. 1,000 people have come, 100 people, or 10 people, it doesn't matter. So the 10th guy came in, there are 10 cookies now, and the fifth guy leaves. Well, the fifth guy, when he leaves, or she leaves, she's going to put a hand into the cookie jar and take out a cookie. It doesn't have to be the cookie that you put in, it's just any cookie, right? So now the count of cookies has gone down from 10 to 9. So each one of you are going to do that. And the last person is going to pick up their cookie and find that it's empty. And that's when they trigger the extra action. So even if we can't see each other, the cookie jar is going to be our common sort of repository, right, of how we view us, all of us, in relation to each other with respect to that light source, right? Am I making sense, guys? So how do we build that is going to be, an interesting problem that has some applications in other places. Like, for example, you want to make your code be concurrent. You want to move on, for example, and use certain parallelized libraries. And so in those scenarios, in conjunction with C++, it gives you some idioms, so to speak, right? It expands your knowledge in terms of how people solve all kinds of different problems. So we'll briefly look at that. And the weak pointer is essentially a problem where rather than containers having pointers that point to objects, sometimes the objects themselves start having pointers, start pointing themselves to other people in the memory. So we call them weak pointers. And so this creates a cycle because object A sitting in memory that got created because we are loading up a new level, It could be a sound file. It could be whatever resource. It's pointing to another object, right? And it has objects that are located, pointers in trees, graphs, and all kinds of other data structures, pointing at itself and pointing to the other guy that this guy is pointing to. Well, the other guys go away. Unfortunately, we end up with this cycle where the cookie jar says 0, but these guys don't want to deallocate themselves because they have these pointers pointing to each other. So we need to kind of think about how that works. So let me show you how to deal with the unique pointer, because that should be your go-to from today, right? You really should not be writing code with raw news and deletes. So which file do I want? Oh, unique pointer. So it's here. So let me first of all show you some uses, how you can use it, because that would be the first thing, right? And that'll give you a sense of how we can kind of design something like this. So I'm going to leave the file up there, but you see my string class. Obviously, we can do this with ints, but it's always better to work with our own type so that we can read error messages. So this is a pointer, guys. Object. It's no longer a raw pointer. So unique pointer is declared in memory, the header file. It is the one that is closest to a raw pointer. So if you're not really interested in sharing, you are the exclusive owner of the pointer that points to this particular object, and nobody else should be pointing to that particular memory other than you or your pointer. Then this is the right pointer for you, right? So most of the ordinary pointers that we tend to use can be easily replaced with unique pointers with minimal effort. Well, actually some effort, and I should have said minimal cost, right? Because they're guaranteed in the sense of being lightweight. Okay, so this is how I normally allocate an object on the heap. Now, generally, we don't tend to do this. So this is a tie program. We never ever program like this. If we have str and RAII class, so there's no need for us to create pointers. But I'm using the game analogy. I'm loading up a level. The level contains lots of information. So the same object is going to be referenced by many different parts of your engine. I gave you some examples: AI, physics, collision, graphics, and I don't know, maybe there are more things. So what we tend to do then is to create that particular object in the free store, in the heap, all right? And normally what you would have had was a pointer that points to that particular object. And using that pointer, what you would have done is that you'd have said, hey, I want, a container of string pointers. When you replace the string pointer with animation data, sound effects, what have you, texture data, anything that is complicated and big. So what you would do is you would say, I would like to kind of, get access to something like this, right? And handling these pointers is complicated, very complicated. Why? Let's say you have 1,000 elements and you don't have any more memory, so you push back a lot of these pointers not these pointers, but pointers, iterators that you had, they get invalidated. So you need to go in and revalidate a lot of those pointers. So this it becomes hard. And this same object may wish to be also stored by the AI system. So the AI guy, maybe I'll just make it be something simple like this, right? Is then interested in getting lists, then interested in pushing back the contents of the first element of this guy. So now we have two guys that both point to the same object. And that is what the sharing part comes, right? In the shared pointer stuff. So we're not really talking about that stuff. So for whatever reason, you need raw pointers, and this is how you deal with it, right? The better way to deal with this since 2014, I think, because I'm pretty sure this wasn't there, is to do something like this: make unique. So the basic idea that a lot of people have is that, hey, we are using smart pointers. We want to get away from raw pointers. So why do I see a new, right? So it sort of creates that little dissonance in when people read your code. So what we do is we kind of essentially say something like this. No, we simply say, what is the syntax? So the compiler gives us some facilities that allow you to kind of create an object of this particular type that encapsulates a pointer to this particular type. So it's quite confusing. So let's say if maybe I should simplify. Hey, you wanted an int pointer, okay? And this is how you go about. Mm. So what's happening here is that UI is an object that encapsulates an int pointer. And that int pointer has been allocated an int which was initialized to the value 25. So anytime you want access to that pointer, well, this gives you the int object, the 25 that is sitting somewhere in memory. If you say UI, well, you're dealing with this RAII class-based object. It's an object. So if an exception is thrown somewhere here, it doesn't matter to you because based on RAII principles, this guy has a destructor, and that destructor is going to basically call the delete operator and delete the int object that was instantiated on the free store. Okay. So if you haven't used smart pointers, then yeah, it looks like this. So here I'm instantiating an object that will encapsulate a pointer that points to this particular block of memory. And we're also saying initialize that block of memory this way. All right. So it has the same interface as an ordinary pointer, but uh, in our case, the string object is encapsulating a C string, a sequence of characters. So PTR is going to mean the object. When you apply the dereference operator, the unique pointer is going to overload the dereference operator. So this means the pointer. So obviously I want to access the individual elements. If I don't use the parenthesis, then the subscript operator, I believe, has the higher precedence, and the compiler may get confused, right? So that is why I had to do what I had to do, which is break the built-in rules and instead say PTR is a pointer. PTR is an object. This gives you the pointer, right? And so I want to access each one of the individual elements. So that's how we do it. And so there's facilities that allow me to iterate through my encapsulated string and access each one of those elements using the for range. Obviously, that's because the string class implements the begin and the end. Notice there are no changes that you need to make to the string class. If you want to use these things, then you just have to follow certain conventions. That's all. Let's see. Obviously, this gives you the string object, right? So this is a object of type unique pointer. This is overloaded, and so you're calling the string pointer that is encapsulated by this guy, and you're calling it size member function. All right, seems like time's up. So I'm going to continue from here. I'll put all of this, and what I'll do is I'll quickly kind of show you guys how somebody might design a unique pointer class just in case, right? If you're from embedded world and you can't use the library, just quickly run through that, and then we'll move on to the shared pointer stuff. It'll be quite useful for you to kind of build, your knowledge in terms of how to design and implement classes that solve certain different unique problems. So that's where I'm going. I'll do that on Monday. All right, and yeah, Brandon, I'm working on the work. It's just kind of it was kind of hard to get everything done the last few days.
Hi, can I ask a question?
Yeah.
Have you discussed the midterms for this subject? Did you say
Yeah,
earlier?
yeah.
Can you repeat it, or like, can we get like a finalized email or something?
Mark 20th.
Okay.
1 p.m.
Got it. Online,
So,
right? Your safe browser?
well, that's the thing. I think I'm trying to figure out the best thing, and I'll let you guys know. And I'm working on it, working on quizzes, assignments, all that stuff, so that you guys are well prepared. And if there's any work to be done, don't worry, guys. I'm not gonna, tell you to complete everything in a little bit of time, right? So I just need to kind of sometimes get organized. And the online grader, I have to research, I have to learn some things in Python that I didn't know. So, each one of these things is a whole that sinks where time goes away in no time to get something to work. But there is progress. So I'll be able to do something in relation to quizzes so that everybody has some review. Because otherwise it seems like it's too sort of theoretical. Uh, and so I'll take a look at all the code that I have given you guys, and then I'll prepare some questions based on that. Okay. All right. It's 11, so I'll let you guys go. I'll see you guys on next week.
Thank you, Professor.
Already.